Heat capacity is the amount of energy required to raise the temperature of an object by 1 degree Celsius. It's the heat absorbed over the increase in temperature. There are two types of heat capacity. Specific heat capacity is the amount of energy required to raise 1 gram of a substance 1 degree Celsius. So the units are joules per degree Celsius times grams, or you can have Kelvin instead of degree Celsius. While molar heat capacity is the amount of energy required to raise 1 mole of a substance 1 degree Celsius. Notice instead of grams, there's moles in the units, so be careful of which one they give you. A calorimeter is a substance that's used to determine how much heat is associated with a chemical reaction. You have constant pressure and constant volume ones. In constant pressure calorimetry, our energy released is equal to heat capacity times mass times delta T, or energy lost is equal to energy gained. Cp is our specific heat capacity, and that's what we just saw was joules per gram degree Celsius. M is mass, usually in grams, and delta T is our change in temperature. So make sure you know the formula Q equals MC delta T, Q being the energy. The only heat capacity that you need to memorize is for water. That's 4.184 joules or 1 calorie per gram degree Celsius. So in this problem we have a coffee cup calorimeter, which tells us that it's constant pressure, or Q equals MC delta T. We know our Q is 596 joules. Our mass was 29.6 grams. Our specific heat capacity, it's water. Our heat was in joules, so we need to use 4.184 joules per gram degree Celsius, and we're looking for the delta T. Plugging all that in, we can solve for delta T. And so that's 4.81. But we didn't want to know delta T, we want to know the final temperature of the water. Final temperature minus initial is equal to the delta T. We know our change in temperature, we're looking for the final temperature, and we know the initial temperature. So solving for TF, we add and we get 27.7 degrees Celsius. You also could have plugged in TF minus 22.9 and solved all at once, but that would have made your algebra more difficult. This one's also a coffee cup calorimeter, but we're mixing two solutions together. So we're going to be using Q equals MC delta T. We don't know our Q. Our mass, we're going to need the mass of the entire solution because they gave us the specific heat of the whole solution. They gave us the density of the solution, which means that we can figure out the mass of our solution using our density equation. So we know our density is 1 and we have 2,000 milliliters. So we're looking for our mass, which means it must be 2,000 grams. We got 2,000 milliliters because we have 2 liters. Each liter is 1,000 milliliters. Our CP was given. It's 4.18. And our change in temperature is final minus initial, or 3.1. We can plug that in and solve for Q. And our unit for this is joules. But notice it wants to know the enthalpy change per mole of barium sulfate formed. This isn't per mole of barium sulfate formed. So we need to have an equation. Barium nitrate reacted with our sodium sulfate to produce barium sulfate and sodium nitrate. Needs to be balanced. And because we had 1 liter of a 1 molarity solution, then that means we had 1 mole of each of the reactants, which means we should have 1 mole of barium sulfate produced. So this was the amount of joules per mole of barium sulfate. Pause the video and try this one on your own. It says it's a coffee cup calorimeter, so we're using Q equals MC delta T. We don't know our Q. Our mass, again, we want the total mass since everything is given in the whole solution. So that's 76.6. Our CP was given. And our change in temperature is given. We want it to be a positive number, so this time we're going to do 25 minus 23.34. Notice the temperature was going down, which makes this an endothermic reaction. Solving for Q, you get 532. But our answer needs to be in kilojoules per mole of ammonium nitrate. Right now, it's 532 joules for every 1.6 grams of ammonium nitrate. So we need to convert these units to kilojoules and to moles. Every 1 mole of ammonium nitrate weighs 80 grams. Now we're at the units of joules per mole. And there's 1,000 joules in a kilojoule. So you get 26.6 kilojoules per mole. Go ahead and pause the video and try this one on your own. But before doing that, a hint. You're going to be doing heat lost by the iron is equal to heat gained by the water. So put all your iron on one side and all your water on the other side. So Q of iron equals Q of water, so MC delta T is equal to MC delta T. I'm going to pause it now and try it on your own. So I'm writing all my iron information down. I know my mass. My CP is what I'm looking for. My delta T is always the same for both substances. So 100 minus 22.7. And then I'm going to have all my water information. And again, my change in temperature is 22.7 minus 21.2. And then I'm just going to set these two equal to each other. And so my specific heat of iron is 0.44 joules per gram degree Celsius. I'm going to pause the video and try this one on your own. If you got D, you got close, but that was grams, not moles. The answer should have been A. See how we got that? We know our Q. We're looking for our mass. We know our specific heat. You know the change in temperature, so you can solve for mass, which is 68.6 grams. Converting that to moles, you get 0.348 moles of gold. And since those were our answer choices, it should have been A. You can try this one. Hint though, you're going to need to use our MCAT equals MCAT though, and put all of one water temperature on one side and all the other water temperature on the other side. Restart when you have it. So we have 20 grams with 4.184, and 80 degrees goes with that one. So we're going to do 80 minus TF, since our final temperature will be somewhere between 80 and 25. And then on the other side we have 20 times 4.184, and then final minus initial to give us a positive number. Remember, you've got to manipulate the temperatures where they're positive values. So on one side you have TF as the second variable, and on the other side you have it as the first one. On this one you can eliminate the 20 and 4.184 since they're on both sides, but if not, you would have to distribute that out and then solve for the variable. Combine like terms. So we have 105 is equal to 2 TF. So the final temperature is 52.5. Notice it's between 25 and 80, which is what we would expect.